I wasn't I wasn't the original presenter for today's class, but the presenter himself is rather busy, so today I'll be substituting for him, and hopefully it'll go normal as planned. So here are the contents we will be covering. We'll be beginning with some research basics and guidelines. We'll move on to data visualization, and we'll be ending with data analysis in Python. So yeah, first of all, we will cover some basics of research. Here we have a research cycle, which you can basically understand as a modified version of the scientific method that's specially designed for mathematical modeling. So, of course, when you're constructing a model, we begin with a fundamental investigation before you even know too much about the subject. And then after that, you move on to constructing your hypothesis based on the investigation. And of course, we also conduct research based on the hypothesis. After we conduct research and develop a model, we go on to the experiment. And then we analyze the results. And basically, we repeat the entire process until we get some analysis and experimental results that we desire. So now I'll discuss each section and some basic guidelines in more detail. So for general investigation, you should learn a lot about the topic aimlessly. And as for why I say you should learn about it aimlessly is because you might have some stereotypes or misunderstandings of the topic because you haven't really studied it in a systematic way before. And so after learning it and after covering some background information to maybe eliminate your previous stereotypes, you can find your subtopics of interest. So basically deconstruct this larger topic into very specific subtopics. And then for each subtopic, we basically repeat this process. But when you're researching a subtopic, you can't actually research the problem itself. What we do here is something that I call looking around the problem. Like you search for things that do not directly answer the question. For instance, if I'm constructing a model of a honeybee colony, I do not search how do you model a honeybee colony. I search, for instance, how does the honeybee population change in the winter, or maybe what factors affect honeybee reproduction in the summer. So yeah, that's basically looking around the problem instead of directly searching for an answer. And when doing this, you should always use a mixture of formal or informal sources. And formal sources will help you gain a very precise and very rigorous understanding of the subject matter, while you'll need informal resources to help you maintain your interest in the subject and also help you understand some of the more technical jargon in the formal resources. You'll also be using a mix of boring and entertaining sources. You should always achieve for a combination of reading things that you don't really enjoy and also reading into subjects that you really like. Because otherwise, if you really like something, then you might have strong opinions, and that may cause your judgment to become biased, and that's not very good. But if you also just continuously read some very boring materials, it's also not very effective because you're most likely going to be distracted. Yeah. And so the final piece of advice when conducting a general investigation is keeping a fixed time frame. So basically, before you even start the investigation, you should set 30 minutes, let's say, to researching this subtopic and maybe 20 minutes for the other subtopic. And even if you feel like the time is insufficient, don't change the time during the investigation. You maybe could pursue a second investigation after the first one. So yeah, that'll help you maintain a steady pace and not be overwhelmed by the workload. And after the first investigation, we can move on to the construction of a hypothesis. For the hypothesis, you should always use very basic logical deductions from what you've learned before. So based on what we learned about honeybee colonies in the winter, we can deduce that maybe the population during the winter will decrease significantly. And when learning about the hypothesis, you should always keep in mind how things work. And in doing so, you should keep in mind this principle called Occam's razor. And so what this means is basically that when you have multiple strategies, multiple explanations to the same problem, which lead to similar results, you should always go for the explanation that seems the most intuitive or simple. And that's because right now you're just constructing a hypothesis. If you're starting with something very complicated already, it's going to get much worse later on, and you're not going to be able to identify the key influential factors in your work. So yeah, start with something very simple, but also clearly explains the phenomenon. And in mathematical modeling, the key difference between most mathematical research is part of the hypothesis is for you to construct your assumptions. Now here, I don't want you to basically list all of the assumptions. I want you to find some key assumptions. If you took the modeling class before, like the basic models from scratch, you'll realize that we started with some very intuitive assumptions and we realized it was insufficient. So basically, we went in a hypothesis cycle, repeatedly constructing and also modifying our hypotheses. That's basically the idea you want to have here. Start with something simple, intuitive, but also works pretty clearly and also is a very rigorous assumption that is definitely needed for your model. And and four, basically, it's what we have mentioned before, is you have to predict basic trends. And in doing so, you should use your common sense. So if you predict something mathematically, or let's say using estimation, and it's very weird, maybe it predicts that the honeybee colony grows indefinitely during the winter, then you really don't want to keep that hypothesis because it can be misleading when you construct the model. And in this step, you should always use Fermi estimates if necessary. Basically, what that means is you shouldn't go very deep into the estimate, but you should use powers of 10. Let's say you can estimate that the honeybee population would probably be between 10 to the power of 4 and 10 to the power of 5 honeybees at any given time. So if somehow you calculated that the honeybee population contains, let's say, 1 billion honeybees, then your model is probably wrong. That's the purpose of constructing a hypothesis. And so now we move on to the modeling process. Here we also want, this is what we call research, basically. So yeah, so here we want to divide the main problem into subproblems. And as for how we do this, there are actually many ways to do this, but I think the most simple one, and I think which is the most useful, is by doing so mechanistically. So let's say, again, let's say we have the honeybee population. And if we're constructing a model, we can consider several distinct mechanisms. For instance, the first mechanism influencing the number of honeybees is the number of births. And the second mechanism is number of deaths. And then we can further divide this into subproblems. We can divide this into, let's say, honeybee deaths caused by predators and honeybee deaths caused by diseases. So for each of these, we can have a submodel, and these submodels are also very independent and very clear. So we can easily construct a miniature model for each of these mechanisms, and then finally, in the very end, we can basically combine them directly and form our final large, robust model. As for when you're developing each mechanism, you should always begin by quantifying the influencing factors. For instance, you should clearly know whether you are investigating the number of cumulative honeybees or the number or the honeybee density or the population density, or maybe just the population itself. So you should investigate how you quantify these factors because sometimes quantifying them in different ways can lead to drastically different results. Also, use logical thinking at each step. I don't think I need to emphasize that. But then I think this thought process is very important. So when you're doing modeling, you should always start at the core. And here the core is basically the problem that you're assigned with. And after starting at the core, you basically branch outwards. It's kind of like a tree, and it's gradually stemming outwards into smaller and smaller problems. Then at the very end, you basically connect all the endpoints of each node. And by connecting these endpoints, you are able to form a very robust model from many smaller ones. And finally, because you're considering a tree, you should always consider backtracking, which is when if you identify a problem in one of the procedures, you can backtrack to find some more basic mechanisms and identify existing problems that may lie within those mechanisms. So you have to keep the tree very clear so you can backtrack at any time and resolve any conflicts or any unreasonable assumptions and predictions that are made. Now, finally, we move on to the experiment and analysis section. For this, we'll be talking more about this tomorrow, I believe. So today, basically, this is a basic overview. So first of all, you should compare your models with reality because models are generally some descriptions or some predictions or something along that line to assist with your understanding of reality. And in doing this, we should make basic comparisons at each step, then construct thorough evaluations at the end. So don't leave all your problems hanging until the end. You should be correcting them and also comparing them with reality at every step of the model creation process. You should also guide your intuition using qualitative indicators. For instance, if you draw a freehand graph, a freehand drawing of the trend, then you might see if it's increasing or decreasing and how sharply it's increasing. So that's some qualitative indicators, and it's very non-rigorous, but it's very important for guiding intuition, and I do recommend that during the process. And finally, when assessing the model, you should focus on quantitative indicators. So you have nowhere to hide and you can face the real problems and how severe the problems are in your model. Of course, more will be coming tomorrow. So yeah, that's the entire research fundamentals section. Does anyone have any questions? If you have them, you can send them in the group chat. I'll basically be waiting for 1 minute, I think. Yeah. If you have questions, you can basically ask them now, or otherwise we'll move on. Okay, it seems like no one has any questions. Yeah, the section was quite basic, so I wasn't really expecting questions, but yeah. And so now we'll be moving on to the next section, which is data visualization. So for data visualization, we'll be using a Python library called Pandas, which will be providing us with a variety of data structures and tools that it will use. So you can download this at pandas.pydata.org, and I'll send this in the group chat. So if you have not downloaded this already, please download it because it'll be very useful when you are constructing your models, and especially when you're evaluating them. Yeah, and I'll also be sending the PBT after class, so you can use that as well. And when writing code, at the beginning of the code snippet, you should always import pandas. And here, the convention is to import pandas as PD. That's basically an abbreviation. And so you simplify it using this form. Just to confirm, everyone has pandas, right? Because I believe yesterday you already did something on simulations, Monte Carlo simulations. So I think you should have installed Python libraries yesterday. Yeah. Okay, so if you have pandas already downloaded, we'll be doing some stuff with that later on. So in pandas, there are basically two main data structures. The first one is called series, and it's basically a one-dimensional list which holds data of any type. And of course, it's an ordered sequentially labeled list, so that makes it very helpful when identifying which data element you're trying to choose. And we also have another data structure which is called a data frame. This is a two-dimensional array, and you can sort of understand it as a table. So it helps us express independent and dependent variables in each of the columns of the table, which will be used later on when we are trying to make some graphs. So the first thing you have to do with using pandas is to load data into a data frame. And this is because we won't be really considering series at all, because we'll usually be considering two variables, an independent and also a dependent variable. And to load data into a data frame, you can do it by direct input, which is given in the first line here. And you can input whatever array or dictionary or nested array you want to input into the closed brackets. But then I don't think we'll be using this because most likely we'll be using data in .csv format, which is comma separated values. So if we do want to input data from a CSV file, we can use pandas.read underscore CSV, and that is a function of pandas which directly reads the rows and columns of a CSV file and converts it into a data frame format. Of course, the good practice here would be to store the result in a separate variable, which we'll usually call df unless otherwise instructed. And we will be putting them under the same file path and folder as our Python program, or otherwise you will have to include a long chain of the file directories, which we don't really want. And to check if the file is loaded correctly, we can print df, which is the data file, df.head or df.in. So that checks basically the start and end of the data file. And if both are correct, we can basically presume that the entire file has been loaded properly into the data frame. If you're interested and if you already have data frame and pandas downloaded, you can try to do that now and see if you encounter any bugs in the process. Because programming usually contains a lot of bugs, and it's usually pretty hard to resolve on your own. So yeah. If you have Python, I'll give you around half a minute to try this. Okay, it seems like no one encountered any problems. So we'll move on for now, and if you encounter any bugs or issues, we can come back to this page and resolve them. Yeah. So now we are coming to the load data section, and this is basically what I wrote, and it does work as shown here. I probably won't be programming in this class today because I'll be switching between Python and Zoom and also the presentation. But if you do have any questions about the programming, I can help later on through Discord or something. Yeah. And so basically we see here, we first import pandas as PD, then we load the data from a CSV file, then we display the first few rows using df.head. And of course, you see here, this is the table that we inputted in CSV format. And then this is the final result that we obtain in the end. And so now we also consider how to filter data. because sometimes you input data and there's some extraneous variables or some stuff that you don't really need. Here, one method is to filter directly. So basically, df and large and in large brackets, you have the filtering standard that you're going to use. And this is going to mainly be in the form of a list of Boolean variables. And this basically tells the program which columns or which rows to eliminate and which columns and which rows to keep. So here, for instance, we have a filter df equals df, which is the input. And then inside, we have our filter standard. So for instance, if we refer to the previous slide, we have the variable one column. And so we are only filtering out the standards or the rows where the variable one column contains a value greater than two. So if we understand what we're doing here, it will basically eliminate person one and it will keep person two. And this is basically how it uses a Boolean variable to store the state of the array and how it eliminates those necessary Boolean variables. Another alternative we can use is to basically delete unnecessary items directly. So here, the filter standard is df greater than zero, which is basically if the element is greater than zero, then it outputs true, and otherwise it outputs false. So this program will delete all unnecessary items or items with value that are less than or equal to zero. And they will be replaced by a null value that you could filter out later on using another program. And here we have a final method of filtering data. Uh, basically, uh, this library comes with its own function, which is called iSign. And it takes a series of values and also a series. And it outputs another series containing Boolean variables and indicates whether each element is in values. So for instance, here we have another example. We take the array df, and here the standard is given by df in column variable 2 that I assign 2 and 4. So basically, this means that if the variables in the column variable 2 are in the list of values containing 2 and 4, then it outputs true, and otherwise it outputs false. So of course, we see that for each of these rows, the value of variable 2 is not in the given array. And so this means it will eliminate everything in the array and it will leave us with an empty array. Yeah, so that's rather interesting. Of course, if you want to test this out yourself, you can do so now. I'll give you maybe 30 more seconds. I think that should be enough time. And if you encountered any problems, you can tell me now before we move on. Okay. So yeah. So now we'll be considering another library to graph basic functions, and this is called matplotlib, which you should have already installed as well. So just making sure do you all have matplotlib installed. This is also going to be very important later on. Yeah. And I'll send this link. And of course, here you'll also be using NumPy because you'll be performing other mathematical calculations. And if you haven't done so, you should download this as well using the instructions found on their installation guide. Yeah. So these are the main libraries you'll be using. Now, what we'll be doing here is I will be showing you how to graph a variety of functions using matplotlib and also using NumPy. So one of the main restrictions we have to consider is that when graphing, the x values are discrete. So we actually have to tell them which values, which x values they have to consider. Wait, someone asked a question. Yeah, okay. I guess you have all installed it now. Yeah. So yeah, because the x values are discrete, we actually have to tell the program what x values we want to consider. And here, basically, NumPy provides a very convenient way to generate those x values. Here, NumPy generates something using line space, and this here basically is how you generate the numbers. So what in the example we have here, it's telling us to start at -10 and end at x equals 10, and then generate 400 values within that interval. Of course, here the x values are all evenly spaced, and if you don't want evenly spaced values for some reason, then you have to manually do it yourself. And with those values in place, we can basically define the functions correspondingly. So if we want to graph a quadratic function, we can have y quadratic equals x squared, which is the expression we have here. Yeah. So with all of that set up in place, we can actually do the drawing. So the first part when you draw is you have to create a canvas, which is basically the area that the drawing will take place. Here we define a plot figure, which is basically an area with a defined width and height. And we also create a plot using the plot function, as shown here. It includes several variables. For instance, it includes the list of x values and also the list of y values. Of course, these are all ordered, so for the first x value, it'll also correspond to the first y value. So you have to make sure you order both of them correctly, which should be by default. You also have the plot label, which is the label of the plot line that you're actually drawing. And finally we have line style, which is basically how your graph will look, whether it's a dashed line or solid line or dotted line. And you can play around with these functions later on. You also have many more line styles included in the library, so you can look at them yourself. Of course, we can also create axis labels, which will be very important in when you are finally constructing our paper. We want the readers to see the x values and y values and what they actually represent. And finally, we also have title creation. We also have some miscellaneous features in the bottom. So for instance, we can use the show legend, and we also have to show the graph. So these two functions are rather extraneous. But the third function here is very interesting because it allows the plot to show a grid. And this grid can be very useful when you are actually when you're doing some data analysis and plotting. So yeah. Usually I would suggest turning on this grid to true by default so you don't encounter any errors or mistake when you're plotting the graph. Yeah, and that's the end of the data visualization section. Does anyone have any questions about that? If you have tried all of them yourself and there's no problem, then I guess we can move on. Okay, yeah. I think we'll move on for now. Now, for data analysis, you'll be using something called SciPy, which is basically a list of algorithms for scientific computing. And you can install it from this link, which I'll send in the group chat. And here, there's no one method to import like before, because for each function, we will be using a different import command and different import code, as we'll see later on. So first of all, we'll be beginning with the most basic function, which is the linear regression function. And this is the import command that you'll be using for linear regression. I'll be seeing the PPT later on, so I won't be copying and pasting this line into the chat. But yeah, basically what it does is it imports this linear regression tool from the library, and then we can use that tool later on. Of course, after we import the tool, we also have to import the data that we're considering. So now is where our previous data frames become handy. And for instance, here we can define x to be the list of variable ones and y to be the list of variable twos, if we still remember what it was from before. And so yeah, for the linear regression model, we also have to import the model itself, which of course is called linear regression. And then we'll be fitting this model, which is a predefined algorithm, onto the data points x, y. Of course, here we also have to consider that x and y are also ordered data sets, because otherwise the model will not fit properly. And that will lead us to the regression equation, which is already given by the model.fit. So after fitting the model has some preset coefficients, and it's given in the form of an array. So if you're trying to find slope, then it's basically the coefficient at position 0, 0. And if you're finding intercept, it's actually a one-dimensional array. So it's also the value at position 0 of model.intercept. Yeah, so this is how you find the regression equation. And of course, after we finish that, we'll be moving on to more advanced polynomial regression. But it basically works in the same way as before. So here, instead of importing linear regression, we import polynomial features, and we import this pipeline tool, which will help us actually construct and compute the polynomial. So for the regression, we first define the degree of the polynomial. And here, for instance, if we are doing a quadratic interpolation, we'll be using a polynomial of degree 2. And here we import a polymodel, which is basically another abstract frame, an abstract algorithm that we'll be using to fit against the data points. And so to construct the polymodel, we use the make pipeline function, which constructs a pipeline corresponding to that function. And basically, it includes polynomial features, which includes the degree of the polynomial, and also the linear regression tool. Now, you may be wondering why we are using linear regression here. That's because it considers the coefficients of the polynomial as linear in its terms. So yeah, it's not really saying that the function itself is linear, it's referring to the coefficients. Uh, and so with that, we can move on. Yeah. So after you construct the model, the polymodel, you can fit it again to the data points x and y. And of course, you can extrapolate the model by predicting the value of the model at a certain x value. And as before, we can compute the coefficients. But now this time, the coefficients will give a very complex array. And so if you're trying to access a certain order coefficient, you should actually sort through the array and see which is the coefficient you actually want. And yeah, I think that's basically it. But finally, we also have some other indicators. So the library metrics also includes a variety of statistical indicators and basically covers everything that we will be needing for the IMMC. Here, let's say we want to find the square coefficient of correlation, R squared, which is a statistical descriptor that basically assesses how well our predictions fit with our actual data points. And so first of all, we have to construct the y predicted values. And so after constructing the y predicted values, we can then compare the predicted value sets with the actual values. And then using those values, we're going to generate an approximate R2 score, R squared score. And finally, we should remember that this value is only approximate for very high levels of precision. So you want a lot of data points for X. And yeah, that's basically it. Does anyone have any questions? This is a very short lesson, so we have quite a lot of time for questions. Um, I don't really think there are any questions. So if that's the case, then it'll be the end of this lesson. Yeah. Oh yeah. So right now, basically what we'll do is we'll look at basic quadratic regression. Well, not regression, basically plotting a quadratic graph as we showed before in the PowerPoint. So first of all, we should import our libraries. And we also have to import NumPy. Yeah, so with that out of the way, we can go on to generate our X values using NumPy. Wait, someone sent something. Yeah, you can use any code editor for this. I just think Python idle is quite convenient. And this is, let's define variable X first. Or maybe, yeah, so choose your variable names properly. And then let's say from -10 to 10. And then with 400 grids in between. Then we can define our functions. Uh, so yeah, we have defined our X and Y values. Now we just have to plot it on our graph. So here what you'll do is you'll create a canvas. using plot.figure, and with figure size is being set to 2. Oh, not 2. I think that's the size of our function. So, can we zoom in or something? I'm not sure if I can do that in Python idle. I think the font size is fixed. I can try though. Wait a sec. No, I don't think the zoom in function works in this mode. No, sorry. Yeah, okay. Okay, maybe I'll write this in notes and then I can zoom in notes. Then I can paste it in idle so you can see it better. So wait a sec, I have to adjust it. Is this better? Yeah, this is not a compiler, but the font size should be bigger. Okay, yeah, and I'll do it here. Then we set the figure size. Let's say 1410. I think it's a pretty default value. Then we actually need to create the plot. So plot and then x, x values, y values, and then we also have to move on to our label, which is going to be, let's see, what should we label it? Quadratic, yeah, and then dash. And then we have to create our axis labels. So we'll be using font.x label. And this basically automatically sets the X label. Let's say it's called X values. Also do a similar thing for the Y label. Yeah. And then with this, we can add a plot title as well. Plot.title. And then let's just say demonstration. And yeah, and finally we have to end with our kind of boilerplate code. Basically, we have to say it shows the graph, dot show, and also shows the legend, dot legend. And finally, also shows the grid. And wait a sec. Now I have to switch back to Python idle. Yeah. Oh, this isn't quite working. Oh, it doesn't recognize the Pages font. So yeah, if you're doing this yourself, please don't use Pages. Just use Python compiler. Okay, there are a bit many bugs, so I have to debug it. a little. Oh, okay, yeah, the labeling is okay. Yeah, now it works. So I'll share my screen now. Wait a sec. Yeah, so this is what it looks like. Oh, wait, I'll also let you see my mistakes as well, if you're interested in my mistakes. So here, um, do you all see this screen? Yeah, so basically this is what the graph looks like. And we can also change, let's say, the precision of the graph by, let's say, adjusting to 800. Although I don't think it makes too much of a difference because 400 is already very high precision for a quadratic plot. And if we reload this, you can see that it works. Good. And maybe the screen sharing is a bit problematic. Yeah, so this is what it looks like with 800, and you can see there's not much of a difference. But let's say instead we change to 80, then it should be more obvious. And we'll do that now, I think. Oh, yeah. Yeah. I think the precision is slightly less, but since the graph is very much regular, it doesn't really show on the graph. And so yeah, if you're graphing a very regular plot like this, probably 80 is enough, which also corresponds to approximately 4 values per per change in X. And if no one has any questions, I think that'll be the end of the class.